So Huffman encoding, what does it do is it calculates half codes using some logic which are shorter than 8 bits or 1 byte. So what it effectively does is it reduces the size required to store the string into the file. It still maintains or retains the information as it is. That's why it's called lossless compression. Okay, so suppose this is the string. The length of the string is 10 characters, and to store it into the memory, what we'll be needing is 10 into 8, that is 80 bits or 10 bytes to be precise. So what Huffman encoding will do is effectively reduce this size. Okay, so let's look at the algorithm first. Okay, so what do is first we calculate. Okay, I'll just write down the algorithm is first we calculate frequency. This is for variable size of length for each encoding. Calculate frequency of each character. Construct hop tree, and the third step is basically encode. Okay, just make it a bit smaller. So what do is scan the string from left to right and calculate frequency of each character. As you can see, I have already done it. A comes 3 times, B comes 2 times, C comes 1 time, and D comes 4 times. So what we'll be doing is we'll be constructing a hop tree. So I'll just okay, so once we have the frequency for each character, we'll be constructing a hop node with respect to it. So the character and the frequency, B is 2, C is 1, and D is 4. So what we'll be doing is first we'll be sorting them in ascending order, that is smallest to largest, and then we'll be combining the two smallest one into a single node. So let me just quickly rub this. So the smallest one is C in this case, and then with frequency 1, B is with frequency 2, A is with frequency 3, and D is with frequency 4. These two, C and B, will combine to make a node with only frequency of 3. Then among 3, 3 and 4, the smallest two are 3 and 3, it becomes 6. Now the only nodes that are remaining is 6 and D4. These are combined to get the root of the hop tree. Okay, so then you will ask me, how do you obtain the codes from here? It's very simple. You just traverse the tree until you hit the leaf node, and if you are going on to the left of any node, then you will just append 0. If you are going on to the right, you will append 1. So let's just quickly write down the codes. So for C, it will be 0, 0, 0. For B, it will be 0, 1. For A, it will be 0, 1, and D, it will be just 1. So Huffman codes follow a specific property, also known as no similar prefix. That is, you will see that any of the codes are not preceding any other code, so they are sort of unique in their own way. And what it does effectively to compress is the characters with higher frequency, D in 4 case, are assigned with the smallest code, only 1 as its code. Okay, so this is the basic algorithm. Let's move on to the code. Okay, so let's look into the code. This is C++ implementation of Huffman codes, and let's start with the main function. Okay, so first we'll be getting the file name, and we'll just storing it, and then with if stream we'll be opening the file since we want to read from the file. This is basically an iterator to iterate to the file and get the text, and then we close the file. So let's start with the build Huffman tree.txt. Before that, I'd like to point out that we have made our own data type, that is node, that is for Huff node, which holds a character, its frequency, as we saw, its left child, that is a pointer to left child, and its right child, that is a pointer to the right child. This is basically a constructor. This is a parameterized constructor. Okay, so the build code function, what it takes is the root of the tree. First we'll be calling the build huff tree function. Build Huffman tree function to get the root of the. So what it does is, first we are going to initialize a map. So what this map is used to do is, as we did it over here, is we store the character and its frequency. So basically this map will be storing from character as a key and its frequency as an integer. That is the frequency map. So how do we do that? Is we just traverse the text from left to right, and we increase the value of key ch, that is the character, into the frequency map. It's as simple as that. You just calculate the frequencies. After that, we'll be initializing a priority queue. So why do we need a priority queue? As I said, whenever we are having 4 nodes, what do we want to do is, whenever I combine 2 nodes, we want the 2 smallest ones to be combined into the next iteration. So how do we do that? Is we keep the priority queue in such a way that it sorts the queue in an ascending order every time a new node is added. And how do we do that? Is we define a custom comparator. These are functions in C++ which can be used to compare the elements of a queue or any other STL type. So we have defined it over here. You can do it with struct or class. So struct compare, this is the syntax, that is, it should return a boolean. Then operator is the keyword. It will take 2 nodes, left and right, and return left frequency is greater than right frequency. So if it is true, then it will return and it will shift it to the right. So this is basically for sorting the queue into ascending order. And this is the syntax for initializing such a queue using the comparator. So then what we do is we make a node for each of the character in a frequency map and push it to the priority queue, and every time it is pushed, the priority queue sorts itself in the ascending order. Now what do we do is, until the priority queue has a single node, that will be a root node, as we saw into the algorithm. Just shrink it down a little. So what do we do is, we take the 2 of the nodes, as I told you, we take the 2 with the smallest, we sum them up, sum the frequencies, and add it to the priority queue itself, and set the left and right pointer of the sum node. And for the sum node, we are using this \0 end of string character to initialize it, that is without any character. And then we just push the sum node into the priority queue. So next time 3 and 3 will be the 2 elements that will be popped from the priority queue. And in the end, when we have priority queue.top, when we are returning that, the single element that is remaining will be the root of the Huffman tree that will be receiving into the node star root build Huffman tree. What is this chrono high resolution clock? This is just to record the start time of the program or encoding function in this case, so that we can calculate the runtime later. Now once we have done with the build Huffman tree, then we'll be having a map for Huffman codes. This is the same map that we created over here, that is character to some binary string. So in this case, character to string. So then we'll be calling the build code functions. We'll be sending it the root, an empty string, and the map. So let's look into the encode text function. Yeah, build codes function. What do we do is we receive the root, the string that was empty in this case, and the map from character to string. These are all passed by reference. If the root is empty, then just return. If the root has no left child or the root has no right child, that is this current node is a leaf node, because only the leaf nodes don't have any left or right child. So once you reach the leaf node, what we do is we just push whatever string we have concatenated into the map with the respective character of the leaf node. So in this case, what we do is we traverse left. Once we hit the leaf node, we push C and 0 into the map. If it is an internal node, if you are going to the left, we'll be appending the string with 0. If you are going to the right, we'll be appending the string with 1. Once we have created this map for encodings from character to huff codes, the next step after build code is actually encoding the text. So how do we do that? Is we take the text to be encoded as a string, the map of encodings that we took here, huff code, and basically for each character, what we do is encoded string plus equal to Huffman code of that string. So say the encoded string was empty initially, then we encountered C. What we do is we just concatenate it with 0. Then say I want to encode actually cab, then we have the character A. We will look into the map, it is 1, and for B it is 1. This is the basic way to encode a string. Now this should have taken 24 bits, but in this case, as you can see, 4 and 4, it was done in 8 bits. If you know the map, obviously. Then we just return the encoded string, that is the encoding function. Now let's look into the decoding function. What we know to decode is the root of the tree, obviously, and the encoded text. So in this case, this one. So what we are going to do is for decoding is first we'll initialize a decoding string, then the current node is going to root. So for character bit into the encoded text, in this case everything is binary, so it is going to be a bit. Current node equal to bit equal to 0. Is it 0? Yes. Then move on to the current node of left child of current node. If it is not, that is it is 1, then move on to the current node ka right child. We'll just traverse the tree, and when there is no left or right child, that is we hit the terminal node, what we are going to do is decoded strings will be concatenating the character at the terminal node. So in this case, if it is 0, then again 0 and again 0, we'll be hitting C, and once we hit C, we'll be decoding C as it is. Then current node equal to root node. Then again we start from the root and do the same process over. Once we are done with the character and once we are done with the end of string character, then we will just return the decoded string. And that's it, guys. Don't forget to free your memory. Let me just quickly explain what this chrono library does, or what is the use of these high resolution clock. Is basically what we do is we note down the start time before we do call some function, and then we note down the end time using this function. And then what we do is to calculate the duration, we just subtract the end time minus start time. This is useful to count the time taken for encoding, decoding, etc. Okay, let us just quickly run the program. So first we'll be compiling it with Huffman Encoder Decoder -O for output, Huffman Encoding, or you can name whatever you want. This is G++ since it is a C++ program. Then / whatever you name, put after -o. Now it is asking me for a file name. In this case, I'll just use huffman.cpp. This is some other file, or let me just use nquiz.cpp. You can see that the entire Huff encoded text is printed out, and this is the decoded text. Time taken was 703 microseconds for encoding and 246 microseconds for decoding. And this is it, guys. Huffman encoding is pretty useful for compression. And thanks for watching.